Hello, this is Dr. Liu, and in the previous video I explained how to set up a projectile motion problem, basically the basics. This is how to solve it. So we start with a horizontal projectile because it is a little easier. This is what we're introduced with, the parameters list. So initial position in x, final position x, initial in y, final in y, and these are the broken down components of initial x and y velocities. This is the final y velocity, this is the time. So these are the equations that you have seen already, and make sure you follow these subscripts. Instead of just saying v0, this is v0x, which is only a component of v0. Okay, so let's do an actual problem. This problem is something that you will need to solve, something similar in projectile motion labs. So we'll project something horizontally out. We'll just use the whole left side to draw a diagram. Oops. That doesn't look straight enough. I think trying to hold a ruler on a drawing tablet is kind of slippery. Okay, that's not very good, but let's just use it. So this is our y-axis. Or x-axis, and we start from here. We project something that just goes horizontally out, but due to gravity it bends down. Eventually it hits here. Okay, so since we don't really need that much space, let's redraw the vertical axis and move everything up a little. Okay, so the horizontal projectile makes it slightly easier. And let's see how to analyze this problem. Here, let's set it right here. Oh, interesting, I didn't move that curve. Okay, second time is better. Okay, so we start from our parameters. So this is what was given. So we'll copy the whole list. Copy. Just have it pasted here so we can fill it up. Okay, so what were we were given the initial position. I wasn't. Well, we're given the freedom to choose our axis. So the initial position can be chosen as 0. So this x0 is 0. And initial y position was given. This is at a height of 1.17 meters. And that's how high the projectile launcher's barrel was from the ground. So initial x is 0, and we don't know where it lands. We're going to make a prediction. And the final y position, well, landing on the ground, so this final y is 0, right? Height is 0 as it lands, so here's the 0 meters. Let's put some units here. And the initial velocity was given as this, so v0 equals 5 meters per second. The initial angle of launch is 0 degrees, so that splits into only a 5 here and 0 here, right? So this is let me borrow something from the previous discussion. So let's paste it. Oh, I think I borrowed a little extra. Don't know how that happened, but things just, oh, I see. Things don't really come across nicely. I think some program developers, software developers need to pick up some backlog bug fixes. So can I still move it? Okay, I can still move it. So let's put these together with the equations because these are important. So let's put them together. So that was from here, the initial velocity x component was cosine 0 is a 1, cosine sine 0 is a 0. So this 5 meters per second splits nicely into just 5 horizontally and 0 vertically. And we don't know the final y velocity, we don't know the time duration. We have 3 unknowns, but we also have 3 equations. So the next step is to put the parameters into the equations. So we start from this equation. So x is equal to 0 plus 5t. Okay, so that's equal to 5t. We can solve it. 2 unknowns, right? X and t. And the next equation, y, the final y is 0, landing on the ground. And initial y is 1.17. Initial y velocity was 0, 0t, minus 1/2 g is 4.9, half of 9.8 t squared. Okay, so this can be solved. There's only one unknown t, and this 0 times t, that's a 0. So let's go ahead and solve it already. 1.17 plus minus 4.9 t squared is equal to 0. So t squared is 1.17, it wasn't, over 4.9. So t, if you square root this whole thing, 1.17 over 4.9. Let's recall our Python calculator. So 1.17 over 4.9. So let's get this one first, and then we'll take that answer raised to the power of 1/2. So the time was 4.89. So let's keep 3 digits, 0.489, sorry, 0.489. So 0.489 seconds. Okay. So now we know the time, we can proceed to solve the first one. But I really hate to go back up here because that just breaks the logic of someone who is just seeing the final product. So let's just hold on. Let's hold on. So we move on to the third equation. Vy equals initial v y 0, horizontal launch, no vertical velocity, minus 9.8. Now we actually do have the time, so 9.8 times 0.489. So we can calculate this directly. Let's get our calculator. 9.8 times that. Okay, so times 9.8. That is a negative, right? I didn't have the negative included, so I need to do the negative. 4.79. Okay, so the negative in front, 4.79 meters per second. So a negative velocity, that makes sense. It's coming down. Okay, so now I like to go back to the first equation. So I'll just call this 1, 2, 3. So I want to do t plug into equation 1. So x is equal to 5 times 489. So roughly 0.5, 2.5, right? Roughly 2.5. So 2.445. If I round to even, 2.44. Okay, so I finally found all the things I could find. The final y velocity was known, was calculated. The final horizontal distance, and also the time of flight. So one more thing I like to do is to see what exactly is the direction of final velocity. and its total magnitude. So this final velocity directs downwards, this v here. I want to know this v equals what, and I also want to know this angle is what. Alright, so how do I do that? I had in the previous notes, right? So once you have your velocity, you just do these. Right, so see if I can copy this without things shifting around. I've been getting that quite a lot lately. So looks like things are definitely shifting around. My square root bars have been moved way down here. I don't know their logic in this, but this is obviously something some developers should work on. Back on top, okay. It's easier to use a mouse to manipulate all these things. Okay, so we have these. We'll just stick them here as formulas, and we'll calculate with them on the next line. So this final v is equal to initial v x squared, because velocity x doesn't change. So that would be this 5 here. So 5 squared plus the final y squared, which is this. I will stay away from squaring that negative sign, just in case I make a mistake. Okay, so 5 squared plus 479 squared. Squared. And take a square root. Raised to the power 1/2. I get 6.92. Okay, 6.92. So the total velocity at the point of impact is almost 7 meters per second. Start with 5, right? Start with 5. And here is this initial velocity. Here's the final. Okay, and then the angle can be calculated from tangent minus 1 Vy. This time we need to keep the negative because we're not squaring it. And the Vx is the initial Vx, right? Vx and initial Vx are the same. So this is 5. And we don't have to add 180 because Vx is positive. So let's use Python again. Arctangent minus 4.79 over 5. So it's a negative 43.8 degrees. Okay, so now the entire problem is considered solved. So you have these 3 unknowns that you solve them all, and also you use your knowledge of the y velocity and x velocity to combine and find the final velocity and its angle with the horizontal. So that was the angle downward, right, with the negative. Thank you.